Well, good day. In this video, we're going to look at a couple of control charts. This video complements my video on the X bar and the R or range control charts. These two have to do with where you have discrete measurement. Now remember, continuous measurement is something you can measure with any degree of precision. Discrete can be thought of as more like, well, for instance, binary, yes, no, or perhaps something where you're counting things, 1, 2, 3, 4, and 5. And in this first example, we're truly doing counting the number of non-conforming units. Okay, so it's a type of counting process. But what we're going to do is calculate the proportion of units that don't conform for each sample. Now, this probably doesn't make sense unless if you go up here and read at the top where I said assume the sample size is 25. Okay, sample size in statistics is always known by a lowercase n, so n equals 25 is what this is telling you, sample size 25. So P, our first of the two charts we'll look at today, P stands for a proportion, or some people consider it a percent. But let's do a proportion. So for a proportion, what we would do here is we say, well, out of the 25 units, 2 of them are bad. So the proportion is 2 over, no, that's not physically type in 2, that's click on 2. Okay, so it is 2 divided by the sample size of 25. So 2 over 25. Let's make the 25 absolute because that needs to change, that needs to stay the same, but as we copy it down we want it to basically produce a ratio for each of these different values in this column. So let me click on that formula again. B5 was relative, so it could change, but E2, which contains the 25, is absolute. The next thing we're going to calculate would be the mean of all these proportions. So easy enough to do in Excel. Grab your average function and select all those 20 different proportions, and so 0.132 would be the mean of those proportions. So let's look at the three formulas I've given for the proportion chart, the P chart. The center line is just equal to P bar, so that's the 0.132. So click equals, do that 0.132, and as I did in my other control charts video, make it absolute reference. And the reason why is, in order to draw a chart in a minute, we want to copy this down unchanging. Now let's do the upper control limit. There's nothing difficult about doing this formula here. The only awkward thing is it's so easy to make a silly typing mistake. So let's take this slowly. Upper control limit says first do P bar. Fine, I click on that and I want you to make every cell reference absolute. So there's P bar. Next in the formula we have a plus sign and then a 3 right here. And then there's an implied time sign there, so let's make it clear that that's times by doing Shift 8. And now to get a square root function, all you have to do is start typing it, and by the time you get to SQRT you find is the name of a formula for a square root. So we'll grab that. We have our parenthesis. So let's look inside the square root symbol. We have P bar again. Okay, make it absolute reference. And then we have parentheses, but let's make that time sign clear by putting it in. And then we have the 1 minus the P bar. Make it absolute. And then we want to divide by n. So fine, we do our slash sign on our keyboard. N, I can click on it. Finally, I have to close the parenthesis for everything inside of the square root sign. And notice they're matched. We have these two parentheses here and the two parentheses further on out. So let's click on that and see what we get. Okay, about 0.33. Okay, good enough. Since we made everything absolute reference, copy it down. And now let's go over here and do the lower control limit. The only difference is there's a minus sign there. So P bar minus, I'll do this one a little bit quicker since it's virtually the same, 3 times, and then square root, P bar again, remember to make these cell references absolute, then times, parenthesis, 1 minus your P bar again, and we close our parentheses before we go and do the divide by the 25. Okay. And let's see. Well, anybody can make a mistake, and please notice I did here. I made a mistake because when I did my parenthesis in the middle of the formula, you see a 9 there. That's, of course, I must have not hit shift properly. So there we are. Everybody makes these silly mistakes sometimes. I think that looks pretty good. Let's click it and see what we get. Okay. That is what I expected to see. A proportion can't be a negative, so in the formula it says if negative, set it to 0. So we have to go and do that. Set it to 0, and then just copy that 0 all the way down. There we are. So let's get a visual look at this by doing a line chart. So select all these values, insert, recommended charts. I have a PC. If you have a Mac, I know that there may be some differences in these. Look at these commands. So what we have are 3 straight lines, our upper control limit, our lower control limit at 0. And I call this a center line, but it's not always perfectly in the center. It would have been if we hadn't had to bring this one up to 0 here. We'll label this. This is our P chart. And what we want to do to make this useful is we now want to track these original p-values by putting them on this chart. If you don't see this funnel here, click somewhere on your chart, which will bring it up. Now click the funnel at the bottom, select data. We see the 3 things that are already on our graph, so we want to click add. And now I can do add series name, would just be the heading for what we're adding. Series values would be all 20, these proportions. And click OK a couple of times, and so we have a P chart. So what this says is the system, as it's set up, this manufacturing system, does not have any point out of control. A point would be out of control if the graph here exceeded either the upper control limit or was below the lower control limit. That wouldn't be possible because you can't be below 0 here. So everything's within these 2 reference lines, control lines. The process is in control. That just means the variation is the normal kind of variation we would get from this system. If we don't like that variation, then it just means we may need to improve our system itself, buy new machines, give everyone in the shop a training course or something like that. Now let's look at the second one. This will be a little quicker since we went through a lot of the basics on the previous example. This is different. We do have 20 samples, but imagine for each sample we're trying to just count the number of defects. Now let me explain by putting a practical example on this. Suppose I'm training to learn how to paint automobiles, okay? So we're in a car painting shop. Well, obviously my boss isn't going to have me go up to a $100,000 car and practice on it. He's probably going to give me a sheet of sheet metal and, after some training, test me on it. So suppose each sample is like a piece of sheet metal where I've demonstrated my painting skills. This would be pretty bad, the data here. This would say that 45 defects were found in the first sample, where, a defect might be a little paint smudge or a bubble in the paint or something like that, a drip. And so what this control chart will do is it will help set up the parameters for the system, so where we can see if each of these measurements is within the limits of the system. So the way we do that, reference these formulas, are pretty easy. The center line, which I'll start here, is just equal to C bar. Well, I didn't do C bar yet. I better do that. It's not there. So I'll do my average, and I'll just get the average of all these counts of defects. That's why it's called a C chart. You're counting defects. So it's 49.9. So fine, my center line, as I said, will just be equal to C bar. Make it absolute reference so that you can go and copy it down. All right, low production values here, but hopefully easy to understand explanations. Okay, our center line, our upper control limit. We'll look in the box for the formula. Again, it will be C bar, make it absolute, and it'll be plus 3 times, so 3 times the square root of C bar, again, every variable cell absolute reference. So that turns out to be 70, which I'll copy, 71, which I'll copy down. And lower control limit, like the previous example, the formula just has a minus sign set to 0 if it turns out to be negative. So I'll do that. C bar minus 3 times the square root of C bar, and it is positive, so we're fine there. And we go and we copy that down. So we're ready to have a look at our control chart. Select this entire control limits chart. I will insert 2D lines. I'll label it before I forget. C chart. So lower control limit, upper control limit. Let's go and add our original data, our count of defects. So click the funnel, select your data. You don't see what you need here, so you need to go and add it. And our series name would be here defects, or C. Our series values would be those 20 values beneath it. And there we go. We chart them. Now notice at sample 14 it would appear that we are probably exceeding our control limit. So let's actually look at the data and see if that's true. At sample 14 we got 72, and notice that is above the control limit of 71. So at this particular sample, the job of management, or even perhaps the person directly doing this process, would be to see what might have been different that time that we could avoid in the future, and sort of eliminate that possible mistake. All right, so that's how to construct the P and the C charts and how to interpret the data from the chart, from the graph. All right, folks, I'll be signing out. And once again, I hope these explanations are helpful to you.